In this segment, we will be considering implicit differentiation, and after this, related rates and inverse functions. In all of these, there's a common theme that you will be taking derivatives, need to take derivatives using the chain rule, and then instead of you will be taking the derivative of some expression and then having to solve for the derivative that you are searching for. So we start with implicit differentiation, and implicit differentiation requires the chain rule. So let me review that. Supposing that you've got z is a composite function, g of y of x. So you've got an inside function and an outside function g, and inside function y. So the chain rule says to take the derivative of this expression, you would have to first take the derivative of g with respect to its argument, which is y, and then multiply by the derivative of y with respect to x. And then in implicit differentiation, what you're going to do is you're going to have to solve for dy by dx. Okay, so for example, y is equal to ax squared plus bx plus c to the 35th power. Okay, so there's an outer function, which is raising to the power of 35. And there's an inner function in red, which is a polynomial. Now, if you want to take the derivative of this, you take 35y to the 34th, that's the derivative of y to the 35th, times the derivative of y with respect to x. In this case, the derivative of this polynomial would be 2ax plus b. Okay. In implicit differentiation, you would have to solve for dy by dx. Okay, so so far we've been dealing with explicit functions. So if you look at these two expressions, we have y of x is equal to some function of x, x squared plus 7. In the second one, you have y of x is equal to some function only of x, 3 sine of 10x plus 9 cos of 144x plus x squared plus x plus 1. Okay, with implicit functions, the dependent variable y is not expressed as a function of x, but you've got some expression which ties together x and y in some way. So x squared plus y squared is equal to 1. We are regarding y as a function of x, so y is an implicit function of x. Y is defined implicitly rather than explicitly as in the previous examples. Similarly, tangent of xy is equal to 2. X and y are tied together through this expression. We don't have y explicitly as a function of x, so we said that y is implicitly defined as a function of x. Okay. Once again, the chain rule, you're going to have things that look like f of y of x, and then you are going to need to differentiate that. So take the derivative of f with respect to y, and then multiply by dy by dx. And then, since y is defined implicitly, you may not know what dy by dx is, and then you would solve for dy by dx in terms of y, functions of y and x. Okay, so let's do the first example. You define y implicitly as a function of x by the equation x squared plus y squared is equal to 1. And having done that, I would like to find the equation of the tangent line at the point 1 over root 2, 1 over root 2. You can check that this point lies on this circle defined by this equation. Okay, so remember, think of y as a function of x. So x squared plus y of x squared is equal to 1. X squared plus, you've got an inner function y of x, which is being squared. And then x squared plus y squared is equal to 1. Okay, so now differentiate. Well, the derivative of x squared is 2x. Now you've got a function of y of x, right? So the derivative of that function with respect to y, the derivative of y squared with respect to y, is twice y. That was the derivative of the outer function. Now you have to multiply by the derivative of the inner function, which is the derivative of y with respect to x. So 2x plus 2y times the derivative of y is equal to 0. Now I'm going to solve for the derivative. So I drop the 2, I divide by 2, I bring x over to the other side, it becomes minus x, and then I divide by y. So I get that the derivative of y at a given x is equal to minus x divided by y of x. Okay. So we wanted to find the equation of the tangent line at the point when x equals 1 over root 2 and y equals 1 over root 2. So the derivative of y when x equals 1 over root 2 is equal to minus x over y when x equals 1 over root 2 and y equals 1 over root 2. That's equal to minus 1 over root 2 divided by 1 over root 2, and that's equal to minus 1. So recall that the equation of the tangent line at x naught y naught is given by L of x is equal to y at x naught plus y prime of x naught, x minus x naught. So here x naught, y of x naught is 1 over root 2. The derivative of y at x naught we found was equal to minus 1. And then we've got x minus x naught is 1 over root 2. Okay, so now we substitute all of these things that we were given or that we've calculated into the equation for the tangent line. So the equation of the tangent line is y at x naught equals 1 over root 2 plus the derivative when x naught equals 1 over root 2 times x minus x naught, which is 1 over root 2. So we get that L of x is equal to y, when x is 1 over root 2, y was 1 over root 2, plus the derivative we found was minus 1 times x minus x naught, which is 1 over root 2. That gives you the equation of the tangent line. Another example. So we've got this equation, xy squared is equal to 1. That defines y implicitly as a function of x. And you know that if you graph this function, the point 1, 1 lies on the graph. Okay, so y is, remember, again, y has been defined implicitly as a function of x. You've got x times y of x, quantity squared. Now, if I apply the product rule to this, then, and I take the derivative of both sides, then I have x times the derivative of y of x squared with respect to x plus the derivative with respect to x of 1 times y of x squared. And the derivative of 1, derivative of a constant is 0. Okay, now I need to apply the chain rule. So it's x times the derivative of y of x squared with respect to y is twice y, times the inner derivative, that's what we're looking for, the derivative of y, plus the derivative of x with respect to x is 1 times y squared is equal to 0. Now, the equation of the tangent line, remember, it's L of x is equal to y of x naught plus derivative of y at x naught times x minus x naught. So that's equal to, y was equal to 1 at the point, minus, the derivative was minus 1/2 times x minus, we're looking at the point 1, 1, so x minus 1. Okay. Last example. Find dy by dx when you're given that y squared plus y plus 1 equals x squared plus x plus 1. Okay. Take the derivative with respect to x on both sides. Now, the derivative of a function of y is the derivative of the function with respect to y times dy by dx by the chain rule. Okay. And the next step, the derivative of y squared plus y plus 1 with respect to y is twice y plus 1 plus 0. And the derivative with respect to x of x squared plus x plus 1 is 2x plus 1 plus 0. Okay. Simplify that, drop the zeros. Now solve for dy by dx. You get dy by dx equals 2x plus 1 over 2y plus 1. And I suppose you are assuming that y is not equal to minus 1 half. Okay. So in the next segment, we will go on to consider the a topic which is called related rates. Again, the idea is you differentiate an expression and then you solve for the derivative that you are looking for.